Okay, our next contestant will be Wilfrid Gangbo from UCLA, and he's going to tell us about the master equation for mean field games.
Yes, thank you for the presentation. It is a pleasure to be here to participate in this workshop, and I would like to thank Katie and Simone for the invitation. So I am going to start with a system of equations which I prepare in game theory, and then I will say what I want to do with it. So here I have a notation. So P2 of RD is the set of mu Borel probability on RD of finite second moment. And I will assume that I am given a function h from RD cross RD cross P2 of RD to R, which I am going to call a Hamiltonian. And I am also given a function G from RD cross P2 of RD to R, which I'm going to call a terminal value. Function. So it will be a terminal value function at time t. So 0t is an interval time interval during which the game will be played. And I am going to take two parameters, epsilon, beta greater than 0. So this parameter, this one will appear in front of a Laplacian, and that one will appear in front of something which looks like a Laplacian. So fix n greater than 2, a natural number. And we want to find ui from 0t cross RD to R. RD cross RD n time to R, such that partial derivative with respect to time of ui at tx minus the sum j from 1 to n, the gradient with respect to p of h. And 1 over n minus 1 the sum j is not I, delta Sj, in a product. Gradient with respect to Sj. Minus h of xi, si, your ui, 1 over n minus 1, the sum Sj plus epsilon Laplacian with respect to x of ui plus beta, the sum over jk, the trace gradient with respect to Sj, with respect to Sk. Okay, so let me pause here and make some comment. And we are going to impose that u I of t, I of capital T, x equal to gi, gsi, 1 over n minus 1, the sum g Sj. And this will be done for I from. Okay, so this term look very strange. Let me check the sign. Minus, minus, plus. So when you are familiar with Hamilton-Jacobi equation, when you write the continuity equation, the velocity is this. And so this whole thing is a directional derivative. So you differentiate ui of t with respect to a path s I of t. You differentiate that with respect to time, and you assume that the si is a flow which came from this velocity. And so this is how you get this strange expression.
So the last term in the product should be gradient ui, not v.
Yes, yes, but if you take u equal to v. This is what I tell my student, that it's not a mistake. I do that on purpose to see if people are following. Okay, so this comes from the fact that you have n player, and each of them are affected by noises which are different. So you have a noise Wi associated to player I. And then this term comes from the fact that you have one noise which all of them share. So this is called the individual noise, and that is called the common noise. Now, observe that here, I can rewrite this expression as the sum over I trace gradient Si. I can write it as Laplacian x ui plus the sum J is not K, the trace gradient Sj, Sk. And this term is going to help you improve regularity. And this term is going to destroy regularity, right? If you like, look at in terms of Fourier transform. But when you add up these two and you compute the Fourier transform, you get psi k minus psi j squared, negative. And so it is non-negative, which means that it should not create singularity, but it should not improve singularity. And if you add this epsilon, when epsilon is strictly positive, then you are back to a situation where you can improve your regularity property. This is why most results on existence of solution, they require epsilon to be strictly positive. Now, the difference between here and there. So here, player I is choosing his strategy. And the other player may do something different. So for the value function of each player, the player I is making some decision for himself, herself. But here, the other player, they have a collective decision which exclude player A. If you replace this by 1 over n, some delta Sj, then you get a very easy, you get an easier problem. So the difficulty comes from this difference. And this is why when you are working with measures which are absolutely continuous, with measures which have no atom, you see no difference between this and that. And this is why you get existence of solution in that case.
A question about the last point that you made. I just want to make sure I'm understanding. So this has to do with the specific structure of the Hamiltonians you have in mind. Because, you know, for example, the way you've written that function, it has knowledge of the location of the point xi. Is that correct? Is that the first coordinate?
Yep.
But the point is that the specific structure of the functions h you have in mind, the fact that it has knowledge of the location xi in the first component doesn't inform when it evaluates the final component, where it's only looking at the darkness is not equal to I.
Yes. And also from the game point of view, from the great point of view, you want to say that people can do what. So if player I decide to do something, people can react to it, but they can do whatever they want. So you want to separate these two. So what I am skipping here is you can write an associate cost function to each player. And one can, it is well known in the literature that if you can solve this equation, if you can find smooth solution, this is equivalent to finding a Nash equilibrium for your game. And so I am going to skip the explanation of the connection with Nash equilibrium and just focus on the system of PDE so that I have enough time to cover over material. Now, for system of Hamilton-Jacobi equation, the viscosity solution doesn't work well. This is something puzzling. And so what people do when we are solving this equation, we are looking for smooth solution. If you are not looking for smooth solution, you could propose, there are various suggestion for weak solution, but not everybody agree on what is the correct concept of weak solution. And so here we are going after small solution and for arbitrary time. So for short time, if epsilon is strictly greater than 0, since this operator is non-negative, you can believe that for short time you have existence of sumo solution, and we are going to take that for granted. Now here are the typical question. I am going to call this the mean field game with n player. Resistance and uniqueness. Of solution. 2. The mean field game, and for T large. So by that I mean arbitrary T. And same question. For n equal to plus infinity. So for that, I need to tell you what it means that n equal to plus infinity. Yes?
I have one more grade. The x superscript I in the second line for the terminal condition. Is that an x? Is that the same as the subscript? Or is it superscript? I guess I just want to make sure I understand the meaning of the superscript versus the subscript.
So what is the superscript?
And look at big G. Look at big G. First component X sub I.
Yes, I usually confuse myself and also,
I'm
also my
sorry to
life.
ask these silly questions, but thank you. I just want to make sure that.
Thank you. So when I was preparing the lecture, I wrote V for the function, and now I am writing U, and later the V will start appearing. So V equal to U. So you can see here that I am dealing with partial derivative, and if I want to go to infinity, I have to tell you what is the gradient in infinite dimension. So the gradient, the Wasserstein gradient have been defined by Ambrosio, Gigli, and Savary, but I am going to propose a different equivalent definition, which look quicker to give. So many people here have used the Wasserstein gradient. So this one is not different from what people have used. So let U from P2 of RD to R. And I am going to lift set U hat of X to be U of X, push forward the Lebesgue measure 0, 1 to D. So for any X is in the Hilbert space, which is the set of square integrable function 0, 1 to the D, RD. So one can check that the application is 1-to-1. So for every probability measure of finite second moment, I can write them. There is a random variable X. I can write them of this form. And so that function is well defined. Now we are in flat space, and I can define what is a sub-differential, what is a super differential. I just use Taylor expansion because I have an inner product. And so we have the following theorem, which is due to myself and to the rescue. If zeta z is in the subdifferential of u hat x, so one can check that when this set is non-empty, it is a convex set. Is of minimal norm. Then there exists psi from RD. There exists a unique psi from RD to RD, Borel, such that I have a factorization z equal to psi composition x. And furthermore, psi is a limit when n tends to infinity. The integral of psi minus gradient of phi n square for a sequence phi n, which is of class C infinity of compact support. And the mu here is x. Push forward. Back measure. So this work was motivated by a claim. Yes.
Just the limit is equal to 0, you're saying, or?
Yes, thank you. Yeah, so I can approximate psi by a sequence of a gradient of function. So this was motivated by a claim by Pierre-Louis Lyon, who said that if u hat is differentiable in the neighborhood of x, then you have this factorization. But when you are working with viscosity solution, you don't assume that you have a differentiability even at a point. You work with sub-differential and super differential. And when you give up the fact that your function is continuously differentiable in the neighborhood of S, you make a one-page proof become a 10-page proof. Now, once I have this, I can choose that as the definition of my gradient. I can call this the gradient. The reason is if the sub-differential and the super differential are non-empty, they coincide. And so when I'm taking an element of minimal norm in the sub-differential or in the super differential, it is unequivocally well-defined because if one of them is empty, I am fine. If both are not empty, I am working with the same set. So as done in converse analysis, I am going to define psi to be the Wasserstein gradient of U. And it coincides with the gradient people have used here during this option. So take a smooth function. Remark. Let U be from P2 of RD to R. And assume that my function is differentiable everywhere. And the set UN of x1 xn to be U of 1 over n with some I from 1 to n delta Si. So if you look at Laplacian, Un of x, if you assume that 1 over n sum delta Si from 1 to n converges to mu. And so I am going to put an n here. Then this converges to the integral over Rd, the divergence with respect to Q. So I am taking Q in Rd. The divergence with respect to Q, the Wasserstein gradient of U, mu. So you can check that this is what happened. And similarly, you can compute this limit. So I am going to call this O. O U of mu. This is the individual noise. Operator. And if you look at the sum, Jk, the trace, the second derivative, Sj, Sk, Un of Sn, this will converge to. So the part where k equal to j, it converges to O of U of mu. And the second part will be the integral over Rd cross Rd. I am going to differentiate twice. U, mu. This is going to produce two arguments, S and Y. Let's call it Q and Q bar. Mu dq. dq bar. And I am going to call this partial Laplacian of U. So this is the common noise. This is a geometric object because you can show that if you take this to bilinear form, I mean, you can just read it from here. If you take this to bilinear form and you apply it to the constant vector, the constant base, then you get this. You can also do the same thing. You take your function, you interpolate, you write identity plus T EI, push forward the mu. You use this interpolation, you differentiate twice, you get this object. And so it is a partial Laplacian, which this information turned out to be helpful in other work, which I am not going to talk about. Now, when we let n go to infinity, we'll be looking for particular solution we'll be looking for U such that UI of X so I don't need to justify that. I can just write my final equation, which is what Pierre-Louis Léon did, and then look at my final equation and say, if I set UI to be that, then it will satisfy that equation. So what I want to emphasize is you can view this passage to infinity as not searching for very general solution, but searching for a particular class of solution. Now, proving that this system of finitely many particles converges to the infinite system, this is another difficult problem, which to be able to achieve that, you need to show that the equation I have not written has a smooth solution. So if you think about a finite element method, when you want to prove a rate of convergence, if you know that the limiting equation has a good smoothness property, then you can compute your rate of convergence. And this is exactly the same thing here. Yes?
Just a quick question. I think for that question, you could put back the I in. It wouldn't make a difference, right? For the limit as n goes to infinity, would it?
No.
Right.
Yes, you are right.
Thanks.
Okay, so let me write what is the so-called master equation. Master equation is find the U from 0t plus RD plus the set of probability measure and RD into R such that DTU of T Q mu minus the integral over RD gradient P H gradient Q U P and mu inner product with the Wasserstein gradient U T Q mu d mu. So this is the directional derivative term. And I need to say something. So this computation which I made them for function depending only on mu. Now, if I have function depending on q and mu, it is going to introduce some extra term. So I am going to write a plus epsilon, the individual noise operator, U, T, Q, mu, plus beta, the common noise operator, U, T, Q mu plus H plus minus H of mu. Union Q U Q mu. 0. With the terminal condition U of capital T. T. So you can check that if you restrict yourself to Dirac masses, for instance, one average of Dirac masses, you can check that you get a hyperbolic system. And so this tells you that there is no way you can expect a smooth solution for a large time, right? Because even in finite dimension, we know that there is no smooth solution for a large time unless we have some structural condition. So the first theorem on this was due to Cardialagate, Larry, Lasry. Assume H is separable. H of Q P mu can be written as H of QP plus F of Q mu. And G and H are monotone. So this means what? It means that if I write the expectation of G of psi1, mu1, minus G of psi2, mu2, this is bigger than or equal to the expectation of G psi1 mu2 if I change the order plus G of psi2 mu1 if mu I is the law of psi I for I equal to 1 and 2. And you can write this in terms of differential equation, which I am not going to do because I don't have enough time. Then they prove that for epsilon greater than 0, the mean field gain as a unique solution. I have a theorem with Everest. If H is a displacement monotone, and I am going to define what it means. No separability required. And T is displacement monotone, then we have a unique solution. So displacement monotonicity means that the expectation of the gradient with respect to Q of G, I1, U1, minus the gradient with respect to Q, G, by 2, multiplied by psi 1 minus psi 2 is greater than or equal to 0. So I have, how long I have left? So, example. Take f of q mu, give a convolution. Last 3 Lyon. Monotone. Means second derivative of the Fourier transform is non-negative. And displacement monotone means second derivative. So for instance, if you take a phi of z equal to z squared over 2, negative phi is what give last 3. Yeah. And phi is what give. So the class of, you have some intersection in the class of displacement monotone and last 3 Lyon monotone, but they are not the same set.
Would you put them together and add now 2 functions? And what is the class that you obtain then?
Yes. So you can show that this condition is equivalent to gradient x mu, plus gradient QQ is greater than 0, displacement monotone. And this is last 3 Lyon. This is greater than 0. So if I want to give you counterexample, I play with this. I take a function depending on Q. I can drive a value up or drive a value down to create displacement monotonicity or destroy last 3 Lyon monotonicity. So when you write the second order expansion of this, you see that this is what appears. And the second order expansion of it here, you see that this is what appears.
In this case, we also have a smooth solution.
Yes, it's smooth. Everything has to be smooth. Otherwise, we don't know the concept of solution if we don't have smooth solution.
Wilfrid, is it then short time?
For short time, you have a smooth solution even without displacement monotonicity.
Right. So these are long time results. Right?
This is arbitrary, yes. Right.
Since we snuck in some questions there at the end, I want to try to keep us on schedule. Maybe I'll ask you if you have further questions. You can talk to us later. Okay, so we have one final talk. I hope we're connected.